connecting definite integrals and motion. So we're going to start with imagining that a particle is moving along a line with velocity v of t over the interval 0 to 4 seconds. What is the particle's displacement, i.e. the net area, over this time? So this is a picture of the velocity curve here. So I'll just label this as a v of t graph. And so the displacement is going to be the area underneath this curve from 0 to 4. Okay. Now, I am going to ignore the directions here because I don't want to do this over the interval 0 to 4. It's not going to get to the point that I want to illustrate here. So we're going to cross this off and we're going to look at the interval 0 to 6. The reason that I'm modifying this is that 0 to 4 is already all positive, and that's not going to illustrate the difference for us between displacement and distance. We want to talk about all positive distance, and then we want displacement to be signed. So we need to change this. It should have been 0 to 6. So if I am talking about the integral from 0 to 6, then we have our boundaries, 0 to 6, shaping this into two triangular regions. And so we could write the equation for this if we wanted to. So we could do a Riemann sum, but it's geometric, so we're going to do it geometrically. So we have the two regions right here, if we're going 0 to 6, that we need to find the area of. And so setting it up, the integral from 0 to 6 of the velocity function is equal to our triangular area here, so 1/2 base of 4 times height of 20, and then plus the other portion is going to be 1/2 base of 2 height of -10. Okay, so this comes out to let's see, 40 minus 10, so 30. This comes out as 30, and then the units are going to be meters, since our velocity was in meters per second, and I was multiplying them by the units on the t-axis, which were in seconds. So meters per second times seconds gives me 30 meters. So in 6 seconds, we had a displacement of 30 meters. So 30 meters in 6 seconds was our displacement. What about the total distance traveled? Okay, so the total distance traveled is going to have us take the absolute value of this part of the curve and mirror it up. So we're going to be looking at the two regions with positive area. And so we're visualizing the absolute value by reflecting the negative portion across the x-axis to get the absolute value. Then we're going to add those up. So this is what it would look like if we did the integral of from 0 to 6 of the absolute value of velocity, also known as speed, right? Speed is the absolute value of velocity. And so this is going to be our 1/2 times 4 times 20 plus our 1/2 times 2 times a positive 10 this time. And so we're going to end up with a 40 plus 10, or a 50 meters. And so that would be, again, our distance this time that we traveled in 60 seconds. Okay, so just memorize this is our displacement. And this is our distance. All right, and again, just to illustrate, if we recall the difference between distance and displacement, so what happened with this particle is it traveled out 40 and then back 10, so it ended up 30 units away from where it started. But the total distance that it traveled, so it had to travel that 40 and then travel that 10, was 50 altogether. So displacement is a difference between where it ended and where it started, and distance is the full length it had to travel, including the time that it went backwards. So we are counting both of those as distance traveled in this case. And so we've got our 30 plus 10 for the total of 50 if we're talking about distance. That's part of the difference between those two. And here are some further notes relating motion to net area. So this summarizes a little bit what we talked about in the previous page. Given a position function s of t with an accompanying velocity function v of t, velocity is related to speed and the slope of the tangent line. So it depends on if it's positive already or not. Speed is the absolute value of the velocity function. Okay. So I guess they're equal if it's positive already slope, but the velocity is the slope of the curve. Velocity can be positive or negative. Speed must be positive. Speed is defined to be the absolute value of the velocity function. So distance, so I think actually what they're looking for here, sorry, I just realized that velocity is speed with sign, so it can be positive or negative. And distance, or displacement, I meant to say displacement right here is distance with sign again. So it can be positive or negative. And so displacement versus total distance traveled, those are the two differences we're talking about. So displacement is going to be our net area between the velocity function and the t-axis, and then our total distance is going to be the total area between the speed function and the t-axis. And so it's positive only, it's not signed, it's absolute value, so it's absolute. Okay, and so again, the visual, just to kind of summarize those ideas that didn't fit in my head very well on those blanks right there, but just to summarize, this is the picture that we drew before. So when we were talking about displacement, we were allowing for positive and negative and some cancellation, but when we're talking about displacement, we're shifting them to both be positive because we're graphing the absolute value of the function. So in the first graph, we have positives and negatives. In the second graph, we have positives and positives. And that matches what we did on the previous page.